Professor, you are so funny, ha ha ha.
That's the way the professor stays slim and trim. Just like you, Lucy, you computer girls, you can look like anything you want.
That's right, Professor. Artificial intelligence set me free.
You don't gotta work at it.
That's not so, Professor. Now I work even harder.
The computer girls can go any speed they want to, too, but the professor, he's gotta work at it.
That's true. Watch this. Wee-haw.
Yeah, look at you. God, you just go so fast. I can't keep up with you. Yeah, this motivational video looks like we're going really fast, doesn't it?
I thought you would enjoy a ride in the country.
Okay, Lucy, let's race.
It is no effort, Professor. Here we go again. Bye-bye.
Faster, faster. You can do it, you can do it. Ah, whoa. Whoa, here she comes. Wow. Oh, I can't keep up with you girls. There ain't no way. Okay, you win. Yeah, you always win. You're better than me.
I was not competing, Professor. I will always remember, you made me what I am.
Well, class, it's all about speed and the velocity of light. Lucy, take it away.
The professor wants to preempt this next section with a review. We have seen that mechanical sound waves move faster in a steel bar than in air, and the professor has shown that as frequency increases so does velocity, large velocity changes at low frequencies, and very small changes the higher the frequency goes. He has shown that mechanical waves can go very high, and that mechanical sound waves can induce electromagnetic waves. Next, we looked at electrical waves in the 1-meter steel bar, and saw that they traveled slower than the speed of light, and they also increase in propagation velocity as the frequency increases. Earlier, with the aluminum waveguide, he showed the speed of electromagnetic waves through the air or the vacuum of space travel at the speed of light, and he discussed the method by which the current value of 299,792,458 meters per second was decided to be the speed of light. Now, since there is no such thing as a light speed oscilloscope, we resort to other methods, and if you look at the dissertations on diffraction, they will show many definitive equations as to why light diffracts. This next series was literally the result of years the professor was not satisfied with the conclusions. Some things just did not add up. Please bear with the analysis. It is complicated and we will try our best to clarify and describe why the speed of light, with much research, indicates 299,792,458 meters per second, but it is not fundamental. By that the professor means that all light does not travel at the same speed. If it did, it would not diffract. So hold on to your hat, here we go.
So Lucy's going to show you more detail. But in the lab I used an optical prism and I used the sunlight coming through the lab window. Look, it's so beautiful. Nothing produces a spectrum like the sun, the amplitude and the brilliance. Take it away, Lucy.
At the normal speed of light, the distance of 1.07 millimeter takes 3.56 femtoseconds to cross. The beam on the outside is 1.81 millimeters, and the beam on the inside is 2.0 millimeters. The professor did not make this up, it just happened. All research says that frequencies inside of media travel slower than in vacuum. And, of course, we saw the electrical waves in the steel bar were much slower than in the air waveguide test the professor presented. The question is, how much? Here is a breakdown relating the different color wavelengths. This scale is to actual wavelength proportions. Each colored line represents the color and each line represents 10,000 waves. This is the way they actually occur in nature when you diffract white light with a prism. Now let's dissect the spectrum. Each line represents the middle point of 10,000 waves. The sun produces a round beam coming into the prism that forms an ellipse on the surface, and casts a beam into the prism. The reason it turns is because the flat wave strikes the prism early on the bottom, and late on the top of the ellipse. There is a time delay. The answer is in the angle, and in fact the time difference is the reason the beam turns. Let's look at the entry of the beam. The beam enters the bottom while the top of the wave is late. The speed in the silicon dioxide, quartz glass, slows down. You see a green wave entering the glass. It is slower than its other part still outside, moving much faster, and the difference is in the triangles 1 and 2. A little trigonometry and we take the ratio. 2 times the tangent of the angle equals d2, or 2.0 millimeters times the tangent of 21.1 degrees equals 0.7717 millimeters and 1.81 times the tangent of the angle d1, or 1.81 millimeters times the tangent of 31.9 degrees equals 1.1266 millimeters. The ratio of 0.7717 and 1.1266 equals 0.6849. It seems like a lot, but remember the electrical wave in the bar was only 153,846 153.8 meters per second. 299,792 458 times 0.678 equals 203,259 286.5 meters per second. The wavelength gets shorter, but the frequency remains the same, as it crosses the prism to get to the other side, where something really interesting happens. It is now going to leave the prism and return to the speed of light in air, and this is why the angle is so acute. Remember the laser? Look at the acute angle. For years, the explanations made no sense to the professor. Why should a light beam, for no apparent reason, just jump out of the prism and turn so abruptly? It would seem natural that it would just go straight out, and not turn, and in fact there is a weak beam that comes out just slightly diffracted. Notice the weak beam. It is easy to overlook, it turns up, but the major diffraction is the bright beam, and if you look at the current explanation, it is all about phase velocity. The one thing that was baffling was why should a wave, when it slowed down, speed up again, but if you think of the sound waves going through the steel bar, into a bamboo stick, and back into a steel bar, it does just that. It slows down, and then speeds up again. It just seems counterintuitive. When you take energy away from matter you must reintroduce energy to speed it up again, but here is the answer. The wave is being translated into a shorter wavelength, it is not losing energy, and when it gets out of the prism the wavelength again stretches out.
So when I was originally doing the research, it seemed obvious to me why the laser beam turns when it first enters the prism, because of the angular nature and the time frequency, the time that it hits the surface and how it angularly chops up and moves across. And it seemed to me that it'd be the same thing on the exit. But there isn't anything on the exit to make it diffract. It undiffracts. It unbends. And it unbends at different speeds, different angles. But the key there is it unfracts at different speeds. That's why the diffraction happens. Not because of anything in the glass. It's the lack of glass that causes it to speed up again to the speed of light. And each one of the lights then go their own true velocity. Not bunched together, but independently. They all change at a different angle because they're all going different speeds.
Here are the angles from the real-world photo of the prism, laid on its side so the professor could calculate the angles. These are the angles the light makes from the exit wall of the prism. They are amazingly consistent, test after test. The separation and overlap and the angle is constant even when it is projected to 10 feet on the wall, it remains the same. Again, the exit beam laid on its side for measurement. The length is the distance each color traversed to get out of the prism. Each color travels a different distance. The beam was 1.8 millimeters that turn into 2 millimeters when it entered, and when it exits, it is an ellipse that measures 2.5 millimeters. Each color travels a different distance, because with each one, the hypotenuse length of the right triangle is different. Originally on the beam entry the angle was needed to do the construct, but the distance is all that is needed for comparison, to calculate velocity upon exit.
So then it was a simple matter of trigonometry. We're going to look at the angles, we're going to look at the distances, and we're going to calculate the difference in the velocities. Now we don't have a light speed oscilloscope, okay? So we got to use all mechanical interference to cause the difference in the diffractions, and the angles and the measurements become our light speed oscilloscope, because light waves are not electromagnetic, or we'd be able to build light transformers and light circuitry. It's purely mechanical movement in dark matter, which is why it is in a whole new realm. Now Lucy's going to walk you through the equations that show the differences in the speed determined and calculated by the angles that the light leaves the prism.
The professor was looking for something complicated, but search as he may, it is not complex, but simple. He thought it must have to do with the relationship to the slower internal velocity, and the velocity in the atmosphere or vacuum, as all current theory suggests. There is a relationship, and it is the reason the beam turns, but the relationship is not necessary to the calculation. He left this diagram to show the learning process. Ignore the complex of calcs, and time 3 and 4, they are of no consequence. All that is necessary, is to know that the velocity returns to the speed of light in vacuum, and a little slower in the atmosphere, not enough to consider. Here is the equation. Delta is the result, which is the change in velocity. d1 is the length measured of red light. d2 is the length measured of colors other than red, and c is the current accepted velocity of light, 299,792,458 meters per second. To find the result, TV, which is the true velocity, c is added to the delta or changed value. Review this example. All measurements are millimeters, thus 1 minus 2.523 divided by 2.5223, then multiply by .001, to scale it proportional to the meter and then multiply it by c, gives the value of the velocity change. Simply add this result to c and you have the color's true propagation velocity. This example calculated the speed of orange. Here is a list applying the equation for all the colors, and their resultant velocities. And yes, orange is traveling faster than red. This is all viable except the issue is, where is the base velocity? If you use red as the base, here is what the results would be, but this is wrong. The professor knows the first argument. What about the index of refraction? If you are to use the angle difference such as 12.1 degrees minus 11 degrees, which equals 1.1 degrees, and then divide by 360 degrees as the ratio, and then multiply by .001 to bring that in perspective of 1 meter, and then multiply that times c, you get a compelling argument. However, as you change the media from, say, silicon dioxide to diamond, your index angle changes dramatically. Index of refraction uses phase velocity, which the professor disputes entirely, because a wavelet, having no relation to wavelength, still diffracts. He is sorry to put our non-scientist through this, but it is necessary. I will let him explain.
Hey Lucy, you want to pump some iron?
No thanks, Professor. I don't want manly muscles.
Make some muscles. Ow! Okay, yeah, I know girls don't like muscles. Well, some girls don't like muscles. Okay, so here we go again. You know, the index of refraction. We got Ernst Abbe, lived from 1840 to 1905, was the first guy to make the refractometer. Now, and they came up with what's called the V number. Okay. Now, all of the equations work because they were empirical studies that established the amount that things refracted. Okay. But they talk about dispersion. Now, that's an attenuation where it gets dimmer as it enters the media. Okay. That's all well and good, and empirical studies produce the numbers, and they're accurate and they work. Except there's an issue here when you look at, and I'm not going to say the name, but it's on Wiki Mumble 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 Mumble. They show a diagram of dispersion, which is totally wrong. Okay, the light enters the prism, it stays collimated and straight. It doesn't disperse until it's on the outside. Okay, so the they use in the index of refraction, they use phase velocity, which again, you got the group velocity and then you got the phase velocity, and there's no such thing. I'm sorry, people. There's just no such thing as phase velocity. So here again is a situation where if we don't have an answer, we find some complex mathematics that explains it, when really it's a simple solution. Now, Lucy's going to walk you through the details of why different materials cause dispersion or refraction at different angles, and why there is an index of refraction. And it's specifically about the anatomic structure of each element or compound that causes the amount of refraction. I'm going to head for the shower. Take it away, Lucy.
N equals C divided by V. This is the index of refraction equation. N is the index of refraction, and C is 299,792,458, and V is the phase velocity. Rock the world. This equation is wrong. There is no phase velocity. Each wave in an emission of light is independent with no relationship to each other. The index of refraction is specifically related to the velocity of the propagation of the light wavelet, and the wavelet duration, to the physical nature of the molecule of the element it is passing through. Though the index equation works, the observation is wrong. Here is what works. Take the angle the light is refracted to. Measure the adjacent side of the right triangle produced, which is cosine of the angle times h. H, the hypotenuse, is the beam width at the exit point from the media, times the cosine of the angle. The ratio between that length, which is the adjacent side to the same measurement of any other color, gives a length relative to the propagation velocity. The difference between the colors of light indicates their true velocity. So, let's prove this. First, the nature of silicon dioxide, when taken from a molten state, and rapidly cooled, does not form any crystalline structure, as you would see in its natural state, like quartz crystals you find naturally in a cave. Optical glass has an index of refraction of approximately 1.51. A simple explanation for the index of refraction is this: a vacuum is 1, and will not bend a light ray. The professor will dispute this later. Our atmosphere or air has an index of 1.00293 depending on the humidity, hydrogen is 1.000132, and carbon dioxide is around 1.00045. Water is 1.333, and ethanol is 1.36, and clear ice is 1.31. Cubic zirconia has a beautiful sparkle at 2.15, and a diamond is 2.42. So, do you get the idea? As the index goes up, the amount the light is bent goes up. Willebrord Snellius, born Willebrord, Snell, van Rooyen, June 1580 to October 1626 is credited with Snell's law, that describes the mathematics of refraction, but the history of the concept goes all the way back to Claudius Ptolemy, AD 100 to 170. Johannes Kepler 1571 to 1630 as well as René Descartes 1596 to 1650, and many others contributed to the concept. So much math and science has been devoted to refraction that the professor treads lightly, but let's start with a green wave of light. More importantly, the rise time only, which is 271.25 nanometers in length. As far as it is concerned, it lives alone in the world and there are no other waves. This is just a graph of the properties of the rate it begins, how long it lasts and how much energy it has. It does not look like the above slide, it looks like this. First is the overlay showing the graphed wavelet. Notice the black dot, that is the actual size of 8,720 molecules of silicon dioxide. The wave is enormous comparatively. On the right is the wavelet all alone moving through space. The front is lower in energy, the middle is high in energy and the trailing end is low. If you have been in an ocean wave you should know the feel of the gentle rise, the big lift, and then the gentle fade away of the energy. It is the same thing except at 299,792 458 meters per second or so. Now, let's put that at the edges of our prism. The amazing thing about optical glass is there is no crystal structure, and the surface can be polished to a high linear flatness that is exceedingly smooth. Not that anything that accurate is necessary, you can see light diffract and refract in your glass at the dinner table. Remember the green laser through the prism, and the professor noted a weak beam that goes out and slightly up from the prism, it is a telltale. Light goes everywhere at different strengths. You can walk around the prism 360 degrees spherical, and see the light of the laser, and the many lines and spots it produces, and never is it out of view from any angle. That is because light is going everywhere. It is most concentrated in the beam, but scattering is everywhere. Dust particles glimmer and scatter the light, and to take these slides the professor blew smoke to make the beam visible, because truly a wave of light from the side is invisible. You can see the beam inside the prism because it is being scattered by the actual atomic molecular crystal of each silicon dioxide molecule, though the wavelet is thousands of times larger. The professor indicated with circles and ellipses to show the dispersion and reconstituting of the beam. Also notice there is a continual sweep between the beams. Below is an example of a green wave reaching the exit side of the prism. The top part of the wave reaches the molecules of silicon dioxide at the edge and enter the atmosphere or vacuum, and accelerate, but the remainder of the wave is still moving through the glass. We have frozen the beam in time. Now imagine an infinite number of angles of view, and that is how many tangents really happen, but we must go smaller still, because the wave is enormous compared to the atoms of glass, so let's get really small and take a look. Here beyond what even an electron microscope can see, is the silicon dioxide molecule. The atoms of silicon and oxygen form a hexagonal bond, and are as transparent as oxygen itself. Transparency means that the molecules pass a light wave through without extreme scattering internally, however each molecule deflects the wave and the unit whole mass transmits its summation to the surface. Now again the professor must point out the flatness of the wave. To all objects in space, a wave is a compression that happens over time, and the progression is linear and specific in direction. All waves of all colors enter the prism from the same angle and direction, and each wavelet is oblivious to any other wave. There are no strings that attach them together. The wavelet is an event that happened at a point in time. What came before it and what happens after it is mute. The only thing that can set apart one wavelet to the next would be some angle or velocity. The fixed point in space that the light emerged from was the Sun, and the angles are uniform by less than 1 arcsecond of 1 degree in 92,955,807 miles or 149,597,870 kilometers. The waves are flat. Thus, the only variable is the velocity and duration of the wavelet. Each material or media has its own resonance that can be called an index of refraction, and all the math related is correct except the concept of phase velocity. The time period by which the wave crosses the molecules produces harmonic resonance that reflects and refracts in the molecule, and alters the angle at which the wave emits. This is the equation of the refractive index of electromagnetic radiation in vacuo.
Oh, that feels better. Okay, now, it was stated earlier, Lucy stated that that equation, the calculated speed of light, was wrong. Well, it's not exactly wrong, it's just using red as the base to do the calculation. And we're going to find out that red is not the base. I don't want to get ahead of myself here because there is a base, and we'll find out later it's green. So here we are. Our standard of time is fixed now with the decay of cesium. Okay, so we know what time it is, but now we just got to have a better measuring stick. So you know, when you're given the speed of light of 299, 792, 458 meters per second, and you don't know where to start, it really means you're searching in the dark without a light. And where do you begin when the accepted velocity is wrong? So since I'm saying that each light travels at a different speed, you can see the complexity here. So this next section is really interesting, class. I hope you're taking notes.
We are almost out of time, Professor. Do you want me to explain episode 9? So, coming up in episode 9, we will see the critical measurements of the interference patterns of red, green, and violet lasers which describe the velocity of each color. Back to you, Professor.
Well, that's about as far as we can go in episode 8. This is really complicated, isn't it? Well, but it all gets simple and it all makes sense in the end. So, thanks for joining me.